Let's see, the leaking container problem. Now, if you see this in a book, it won't be this complicated, okay? So let's look at how you would probably actually use this problem, or actually use this solution with the approximations. Okay. So when you're looking for approximations in a physics problem, anytime you see 1 minus something, that's like a raving red flag. Make an approximation here. Anytime there's like 1 minus a ratio to some high power, screaming, make an approximation. Because when you look at this, if it's a big tank, you would imagine this radius is probably like meters. And you would imagine the hole is like a millimeter. Okay? So 1 is if the hole is small compared to the tank. What do you have? You have R is less than R. If R is less than R, then R to the fourth is a whole heck of a lot less than big R to the fourth. And in that case, 1 minus R to the fourth over big R to the fourth is basically still equal to 1. Right? So it's 1 minus some teeny number. If it was 1 millimeter and 1 meter, that's 10 to the minus 3 to the 4 is 10 to the minus 12. Right? So instead of 1, it's 0.99999999999. Close enough. We only want 2 significant digits. So that means this thing is basically 1. So now it simplifies to V2 is just the top square root. That's not so bad. 2 times P minus atmospheric pressure, because that's the top's pressure, whatever it is, atmospheric pressure down here, over the density of the water, plus 2GH. So you'll see books solve it that way. Okay, or give that expression. But they won't show it to you mathematically. They'll just say, well, it's a big tank. The top isn't moving that much. Call V1 0. That'll be how they do it. So I'm just trying to show you mathematically where it comes from. You can use continuity to get V1 and later realize, oh, V1 is really slow. Right? The quicker way would have been to just not have this here. Right? We could have just said, oh, V1 is slow. Because the tank, the water in the tank is barely moving down as this little millimeter hole leaks out. Okay. Okay, so now we're going to demo it. We're going to do an IV problem, but let's do one more approximation. Right? So here I said, maybe it's closed, maybe it's pressurized, maybe it's a fire extinguisher, whatever it is. But let's say another approximation. What if it was open? Then P equals P ATM. Right? Because the outside's at atmospheric pressure and the inside's at atmospheric pressure. Right? So what's the expression going to do then? This is 0. Right? Be good at algebra. And V2 is the square root of 2GH. Does that sound familiar? Like something you might have seen when you're studying for the exam, right? So if you drop something from a height of h and ask how fast is it going when it gets to the bottom, it's going the square root of 2gh, right? mgh equals 1 FMV squared. Solve for v. The m's cancel. The 2 goes the other side. Take the square root. 2gh. So that's a little expression you see all the time. And the reason it shows up now is because we've turned this into basically just a drop the water problem, right? Is we've said the pressures don't have any difference. The kinetic energy at the top is nothing. We basically just drop the water a distance h and ask how fast is it going. Right? So that's why it simplified that far, as we kept simplifying the problem to basically just dropping water. This is just drop water. Now your problem, a real problem, might have much more subtleties going on. The top might be pressurized. Maybe the hole is big compared to the container. But if you get these simple enough, it just looks like conservation of energy because it is conservation of energy, right? That's how we got this, right? That's the reason. Pressure was the work. Rho GH is a potential, yada, yada. I can show you that this is true. So here is a water bottle. It looks fine, right? There's nothing coming out of the water bottle. Oh, but I put a hole in it. Here it is. Ooh, there it goes. I was hoping you could hear it. Let's see. Oh, we have a resonance in the water bottle. Do we? Oh, that's bad. That's got to be the water bottle. There's no speaker over here. Okay, that's free. You have to take 126 now. Okay. So it's coming out. Why is it coming out? Because this is what we just did. This area is big compared to the hole, so if you wanted to calculate how fast the water is coming out, it actually would just be square root of 2gh, because it's open. Now, what if I close it? Don't do it. Oh, I'm going to do it. Here we go. We're going to close it like this. What's it going to do? Think about what you think it's going to do. Oh, it goes really big. It stopped. Completely stopped. Why did it stop? Nothing's coming out. Why is velocity 0? Let me take the thing off. Oh, there it goes again. Now it's square root of 2gh. How did it go to 0 just because I put the lid on it? And nothing. How did it go to 0? Let's see. Why did taking the lid off have to do with it? That's what we're doing right now. I'm glad you're wondering. Why did it go to 0? How could this expression possibly give you 0? Anybody want to guess how you could get 0? Well, one thing, you could set it equal to 0 and solve for something, right? So what's happening, and I'm sure you've thought of it, you just don't want to say it out loud. What's happening is when I put the lid on, this is going below atmospheric pressure. Ah, yeah. So we must be creating a vacuum, well, not a vacuum. We must be lowering, like when I have it open, these are equal. 0, you get some flow. But when I have the lid on, it's pulling the air down, it's expanding the air. We don't want to talk about gases, but it's basically expanding the gas and reducing the pressure below PATM. So this is negative. You can't have negatives under a square root. Oh my God. Yes, you can if you add it to a positive. Okay? So this term is negative, plus a positive term gets down to 0. And then the flow goes to 0. Okay? It's okay. We had a negative under square root. It was part of a sum. Okay? It can't go further down because then you would have a negative under the square root. So if it kept flowing, when this pressure went down, we'd have a negative under the square root and the whole thing would be imaginary. Whoa, right, that would be weird. Let's make sure that doesn't happen. Okay, if it doesn't stop, the whole world's going to go imaginary. Oh, we had a good run. Oh, it stopped. Okay. You don't have to have a lid. There we go. I'll put my hand on it. Now, why does it go big when I put my hand on it? Because I'm pushing on it. But if I hold it long enough, your academic trajectory again. And down to... I love you so much. I'm just kidding. Oh, I pushed too hard. So now I'm like holding a vacuum, and it actually sticks to my hand. Watch this. Whoa. No, okay. That's my hand. Okay. All right. Okay. So this behaves completely, every approximation. It behaves exactly. If we could calculate the velocity, it would just be the square root of 2gh, because this area is bigger than that area. So I encourage you to put a hole in your water bottle and do this. Now you think I can put a hole in the water bottle and walk around with it. So I walked around like this, carrying it around, and I got here, and I was like, oh my God. Because if you squeeze it, the water comes out like that. So I got here, I looked pretty, I looked like I need what's in the next example, which is about catheters. Okay, so let's do the catheter problem.